By the spring of 2003, the builders of the new California Department of Transportation headquarters have spent 10 months digging, redesigning, shooting, lifting, bolting, and welding on what will be a 750,000 square foot office building in downtown Los Angeles. The internal steel skeleton is topped out, and now it's time to put a face on the structure. Give it an identity. Some believe what a structure looks like is the most important aspect of any large modern edifice.
The skyscraper is a symbol of economic power, willpower, technological innovation, all bound up in one highly visible structure that defines the appearance and character of our cities.
Architects have always used diverse materials to give classic buildings character. Terracotta on the Woolworth Building, stainless steel on the Chrysler Building, or glass on Lever House. Tom Main of Morphosis Architects chose to set the Caltrans building apart by cladding it in perforated aluminum panels. It's not only an aesthetic decision. The panels will also help conserve energy by shading the structure. But before workers even begin to enclose the building with windows and walls, the general contractor has decided to construct what's known as a mock-up to test the exterior systems. Mock-ups have become more popular with builders and architects in the last 30 years.
We got a lot of smart people working on this, and they've got some great ideas, but we need to validate the design so that we ensure that it really works, because we only get one shot at it out there on the actual building.
This particular mock-up is a 3-story, fully enclosed structure, complete with window units and an exterior membrane. Dana Nelson is in charge of subjecting the mock-up to several torturous tests here at Smith Emery Laboratories, an independent testing facility located in downtown Los Angeles.
We will test for air infiltration, static water penetration, dynamic wind, structural loading, positive and negative, seismic earthquake testing.
The idea is to subject the mock-up to as many extreme situations as possible to make sure the construction materials, like the window units, and the installation techniques will perform as intended when applied to the Caltrans building. For 3 days, Dana throws everything he's got at the mock-up.
This particular piece of equipment is a pre-World War II Pratt Whitney R2800 2,000 horsepower airplane engine with a 13.5-foot prop. What we use this for is dynamic wind testing. It moves a lot of wind and a lot of water.
The fan creates a 63-mile-per-hour wind. Add some water, and that's just this side of a Category 1 hurricane. While the man-made storm rages outside, inspectors on the inside look for leaks. If there's water, there's a problem.
Tom, or church, here, we got some water here. We got to find out where it's coming from.
To everyone's disappointment, the mock-up appears to be leaking.
Because it's dry.
The chore now becomes diagnosing the problem.
It is just a puddle, probably 2 inches in diameter.
Is it a materials failure, an installation problem, or a design flaw?
Here,
wet on the left side
right.
of the thermostat.
And it's not.
This whole south end was fogged up, so all the mullions were a little wet.
Will the leaking issue be a major setback or require only a minor adjustment? It's not immediately clear.
They left all to be dry.
Mock-up testing like this can help to prevent potential problems with the exterior cladding. But testing the structural system of a building on a large scale is much more difficult. A small mock-up doesn't necessarily react the same way a full-sized building will. There are even a few rare examples of buildings going up before a structural problem is even diagnosed. One of the most extreme examples is that of the Citicorp Center in New York City, where builders had to deal with the potential collapse of their finished structure. In 1978, the newly opened Citicorp Center seemed to hover 10 stories in the air on 4 legs. But unlike a table, the building supports were placed in the center of each wall. The building owed part of its radical design to St. Peter's Lutheran Church, which had occupied the same corner since 1904. Developers wanted to buy out the church so they could have the entire lot to construct their building. But the congregation didn't want to give up their house of worship. Renowned structural engineer William LeMessurier came up with a way of satisfying both parties.
Finally, I said, the solution to this problem is to put the column in the middle of each side, and then the building can cantilever out, hang over the church.
Citicorp offered to tear down the decaying St. Peter's and build a new church, above which they would construct their 59-story skyscraper. The building performed its magic trick with the help of giant V-braces that transferred the gravity and wind loads to the center columns. The building was completed in 1977 and opened to much fanfare. But just months later, the structural engineer on Citicorp got a call from an inquisitive engineering student.
He wanted to know why didn't we put the columns in the corners like a sensible person would do. And I explained that we developed this triangulation system to bring all the loads to the middle of each side instead of to the corners.
The V-braces also helped the building withstand perpendicular winds hitting the building head-on. But the phone call got him thinking. Shortly before the student's innocent call, LeMessurier learned of a design change that now concerned him greatly. To save time and money during construction, the steel subcontractor had suggested using bolted connections on the V-bracing instead of the welded connections originally called for. Changes like this happen all the time on big projects. The modification met building code, and LeMessurier's office and other parties signed off on the alteration. But the bolted connections, LeMessurier now realized, were especially susceptible to quartering winds that hit a building from a 45-degree angle, putting greater stress on two sides.
So I made some calculations, and I found out how strong these bolts were, and I said, oh my, we are in big trouble. Because a wind in a typhoon and hurricanes and so forth would develop forces that would be far beyond the capacity of these bolts, and that the building could fail.
Wind tunnel testing confirmed his worst fears. A sizable windstorm, the kind that hits New York about once every 16 years, could topple the building. William LeMessurier, a renowned structural engineer, now faced a dilemma. Should he speak up and risk his outstanding reputation, or shut up and potentially risk the lives of the building's occupants?
Here I have this knowledge. I have to do something about it.
He alerted the owner of the building. LeMessurier and an assembled team devised a way of reinforcing the susceptible connections by welding 2-inch thick steel plates over them. Welders worked feverishly under the cover of night to avoid alarming the building's occupants. Then, on September 1st, 1978, LeMessurier got the weather report he was fearing. Hurricane Ella was headed straight for New York City.
I was scared to death because we weren't quite ready yet. You see, we hadn't completed all the welding that needed to be done.
Fortunately, the storm changed course, and the building averted possible disaster. Within a few weeks, welders completed retrofitting the building. And today, the structure is stronger than ever, as is William LeMessurier's reputation. The Citicorp incident has only added to his fame. It's hard to know what difference a mock-up might have made for the Citicorp Center. But in Los Angeles, the Caltrans mock-up testing is at least preventing more minor exterior issues.
Okay, it's not where the splice is at. That could be.
But after 2 days of testing, there are still questions.
Over that 1 inch angle, and that's impossible.
Yesterday I was holding my hand and it was completely dry.
I don't see no rhyme or reason why it's there.
The static water test earlier, we had a couple problems with. We think that we've isolated them and we made some repairs, and as we go through, we'll repeat it until we get a clean test on every element.
It will take further testing to find out if this little leak will turn into a financial drain for the general contractor. They've got to work fast. Construction on the wall system begins in less than 2 months. From the decorative buttresses of the neo-Gothic Tribune Tower in Chicago to the sleek lines of the Art Deco RCA building in New York to the glass facade of the John Hancock Tower in Boston. Architects of tall structures have struggled to create exteriors that were as memorable as the buildings were massive. LA's Caltrans building is no exception.
We're putting it at First and Main. It's literally the center of the city, because it's a great site, right? It's a conceptual, historic center of the city, next to City Hall.
An architect has to weigh practical, financial, and aesthetic considerations during design. Struggling against often opposing objectives, the architect sometimes, miraculously, creates art. Skyscraper architects today have over 120 years of successful and not so successful creations to look back upon and learn from. Since the first skyscraper was built in the 1880s, distinct styles emerged as a reflection of the times and the technology available. But they were shaped by building regulations and egos as well. Many scholars consider Chicago to be the birthplace of skyscrapers, and the designer Louis Sullivan to be the father of skyscraper architecture.
The most famous name for the beginnings of the skyscraper is Louis Sullivan, a Chicago architect who came up with a formula for the tall building that accentuated its verticality. He said that the skyscraper, or the tall office building as he called it, should be tall, every inch of it tall. It should be a proud and soaring thing.
Sullivan expressed these opinions in his Wainwright building.
Louis Sullivan had the idea to treat a building like a classical column with a base and a tall shaft and a capital. So the early skyscrapers have a base of 3 or 4 stories and then a very tall shaft, and then usually some sort of a capital, which would be a cornice or a slightly set back top floor or a big ornate roof.
But that's as close to classical form as Sullivan came. He and other Chicago architects like Daniel Burnham searched for a new and uniquely American style. It came to be known as the Chicago School.
The first Chicago school of the 1880s and 90s was represented with a kind of aesthetic theory of simplicity that made the buildings look simple in comparison to their counterparts in New York, where New York architects were much more wedded to historical style. One thinks of Cass Gilbert in the Woolworth building, called the Cathedral of Commerce. And it's a neo-Gothic building. That language of historical styles was much more popular in New York, whereas the Chicago school was called, in its time and by subsequent scholars, a real American architecture.
Upon its completion in 1913, New York's Woolworth building became the tallest skyscraper in the world at 792 feet. By the early 1900s, the streets of New York were becoming urban canyons, flanked by towering spans of glass and stone. Seeing the negative effects of overbuilding, people started calling for construction regulation. The new Equitable building, completed in 1915, was one of the last straws. The The massive structure rose 40 stories, straight up like a cliff, casting a 7-acre shadow across the city. Fearing other buildings like it would suffocate the streets below and decrease property values, New York passed a groundbreaking zoning ordinance in 1916 to limit the mass of buildings.
The 1916 zoning law in New York was tremendously important for the formal development of the New York skyscraper and gave us the characteristic form of the setback tower, a kind of stepped pyramid, a ziggurat, or a setback form that some people call the wedding cake.
Under the new zoning ordinance, a building could only rise so high before stepping back from the street. The higher the building, the more setbacks it required. However, setback laws didn't restrict building height. A tower that occupied no more than 25% of the lot was allowed to rise as high as technology could push it.
When you think of the classic 1920s towers like the Chrysler Building or the Empire State, those slender spires rising from a kind of pyramidal base are the characteristic Art Deco skyscraper of the 1920s. And their form is really dictated by a template, a three-dimensional template that's decreed by the 1916 zoning law.
Sure, the New York towers of the 1920s and early 30s were tall, but they were also extravagant, reflecting the exuberance of the Jazz Age. Perhaps no building captured the excitement of the era better than the Chrysler Building. Built by automobile magnate Walter P. Chrysler and designed by architect William Van Allen, the Chrysler Building borrowed its motif from its namesake's product. The building came complete with hood ornament gargoyles and hubcaps. Although a favorite among New Yorkers today, the building was criticized by many as being too flamboyant when completed in 1930.
And it becomes so large that it's just kind of a sculptural device. And these are all lit from below, and they just glow. It's literally, there are these concrete pieces.
Although the architects of the Caltrans project won't be pushing the envelope as far as William Van Allen did with the Chrysler Building, they're still confronted with the same challenge: how to create a memorable and satisfying public face for a very large structure.
It's also complicated. Something you hate today, you actually admire 10 years later. And we can't worry about working in reverse. Let's do a building that nobody doesn't like. It's totally stupid, because now we produce everything that's just in a neutral. We're going to all go to sleep as a society, because you have a whole series of buildings now that nobody cares about.
But when you see the skin and you look at the real one and you realize it has holes in it and it builds up colors and the thing behind and this, and then you layer light on it, it could work.
Tom has high hopes for the extreme-looking cladding of perforated aluminum panels he's chosen for this building. As Tom and his team struggle with the last remaining design elements, Clark Construction is trying to figure out how to get 306,000 square feet of glass produced, windows assembled, and units transported from the heart of Texas to Los Angeles. They've got 3 months to make it happen. After 10 months of construction on our Caltrans building, features are emerging.
When the steel is erected, you can start reading the shape of the building. It's not enclosed here, but you can see the major volume and spaces. Here there is the dining area, this is the cafe. Just in front of the main entrance of the building, there is a huge light well, which is bringing the daylight through the building all the way down to the urban lobby. So if you look up, you're gonna see this skylight.
Once the structural steel is up, the next step is to enclose the building with walls and windows. Framers start building the walls by attaching metal studs to the steel beams to create the base for the wall system.
Right now, my partner and I, we're going to start setting up the stud for the exterior wall. We have a laser with a tripod that's gonna establish the level line. We're looking for 11 1/4. I have 12 1/2. Go up, partner. Just right there. 11 1/4. Money. I like it. Clamp it.
The exterior wall system is a combination of multi-layers. It starts from the metal stud framing. This sheathing board provides another layer in which this single-ply roofing membrane is applied. This is ultimately the base waterproofing of the wall system.
On this project, Morphosis architects are using a material called Sarnafil. It's a thermoplastic membrane, usually used for roofing. But Morphosis is applying it on vertical surfaces. It's like wrapping the building in cellophane.
They apply the glue, lay the matting over the top of that, and then work out the bubbles.
These walls are known as curtain walls because they hang from the building and don't support any real weight. Nearly every large building constructed since 1900 has used curtain wall construction. Made possible by the introduction of the internal steel cage in the 1880s, the curtain wall gave architects even more freedom of expression. Because they weren't load-bearing, the curtain walls could be light, thinner at the base, and provide larger window openings. And having larger windows was an enormous benefit in an era before air conditioning and efficient electric lighting.
One never had a floor space in a first-class office building that was farther than 28 feet from the outside window to the interior corridor.
Chicago's Reliance Building, completed in 1895, was a fine example of early curtain wall construction and a predictor of things to come. The building's massive windows attracted doctors and dentists whose work depended on good light.
Actually, they had problems filling the building originally when it first opened. They'd never seen such construction with so much glass on the exterior. And Chicagoans thought the building was actually going to blow over in the Windy City.
Fortunately, the Reliance Building never blew over. And after extensive renovation, the Hotel Burnham now invites guests to peer out those same large windows at the city below. Windows are just as important in the construction of today's buildings.
These are the strip window units we're installing out here at the Caltrans District 7 headquarters. We have around 1,000 of these to put in. The weight of that unit's figured right around 300 pounds. So we got 4 guys on it. Every guy's lifting a reasonable amount.
These units are surprisingly sophisticated, double paned, and coated with an energy-conserving film that reduces heat transmittance. But it takes many players to create this space-age product. The window units begin their 1,500-mile odyssey in Wichita Falls, Texas, where PPG Industries, the nation's leading glassmaker, produces the raw glass.
The process of glass starts out with the raw materials area where we load bins with the raw materials. The main ingredients are soda ash and sand. We mix all the materials together and we basically pour them into a big furnace, which we call the tank. The temperature varies between 2,600 and 2,900 degrees to melt all the raw materials. At that point, it pours into what we call the float bath, where the molten glass actually floats on top of liquid tin. The temperature moves from about 2,000 degrees down to about 1,100 degrees at what we call the lift-out roll. It goes up onto what we call the annealing layer. The annealing layer cools the glass down. And then the glass is cut to size in the cutting area we call the wear room. Some of the plants can be a quarter-mile long.
Once the glass is cut, PPG applies a low emissivity, or low E, energy-conserving coating. coating lets visible light in, but blocks 90% of infrared heat, thus reducing heat transmittance. Acura Systems of Sunnyvale, Texas, is responsible for assembling the window units.
We fabricate the pieces, cut them to length, do all the fabrication. A job like the car fan job has over 2 million pieces that we have to produce.
After a 3-day drive, the semi pulls into the Caltrans site. Another truckload down, 72 truckloads to go.
A building without windows in it sounds like jail. There's kind of a sense of freedom to be able to look out. Even though you might have to be at your job all day long, you do have some sort of a connection with the outside world.
That connection with the outside world got an enormous boost when in the mid-20th century, architects started cladding buildings from top to bottom in glass. It was the face of the future, and it would dramatically change the look of the modern skyscraper. 5 months after topping out, the guys with model glass are 85% finished with the installation of window units. The glaziers have moved to the south side of the building, which has much larger floor-to-ceiling window units.
We're going to set all these outside windows on this bottom track, but they're about 500 pounds, so we got to use a cup manipulator, and that just takes the weight because they're too heavy to set by hand. Hold on, we're hooked on the side there.
The love affair between skyscrapers and glass began in earnest with the economic explosion of the 1950s. But one building was decades ahead of the trend. The Philadelphia Savings Fund Society building, completed in 1932.
The PSFS building was the first skyscraper cast in the international style, the language of developing modernism in the 20th century.
The PSFS building was designed with sealed windows and no ornamentation beyond the 27-foot-tall bank letters on the roof. Influenced by European functionalist design of the 1920s, it was a dramatic departure from contemporary skyscrapers, such as the Empire State or Chrysler buildings. American architect George Howe and Swiss-born partner William Lescaze created a building to project the bank's image of luxury, functionality, and modernity.
PSFS had the qualities that predicted the direction that modern architecture would go after World War II.
In the 1950s, after years of depression and war, an economic boom sent skyscraper construction soaring once again. This time with a fresh, modern look. Dubbed the International Style, architects embraced steel and glass, minimalism and function.
There was a new kind of building, a welded steel frame, a glass facade that was hermetically sealed in effect. No longer windows that opened, but a well-tempered environment with air conditioning, mechanical systems, fluorescent lights.
In 1952, the Lever Brothers Soap Company completed Lever House on Park Avenue in New York City. The cool green-tinted glass and stainless steel exterior projected an image of cleanliness and purity. Just right for a soap company. Lever House was one of the first all-glass curtain skyscrapers and would come to epitomize the international style. Across the street, a few years later, Philip Johnson and German-born architect Ludwig Mies van der Rohe collaborated on the Seagram building, an austere, elegantly simple black box of a skyscraper.
Mies van der Rohe was an enormous influence on post-war American architecture generally, and certainly on the skyscraper. His maxim, less is more, became an influence on so many architects.
Through the 1960s and 70s, developers built hundreds of glass-encapsulated skyscrapers with minimal ornamentation.
Architects purposefully avoided all symbolic qualities on their buildings. The most famous buildings of that period, like the Sigras building, are all flat-topped, and they are rectangular, abstract boxes, which I understand the roots of this. I happen to believe that it was a mistaken notion applied to tall buildings. I believe that you cannot avoid the symbolic qualities of a building when it reaches the sky.
Finally, by the mid-1970s, architects were once again ready for something new.
Late in the 20th century, architects start to think beyond the stripped-down modernist box. Philip Johnson designs the AT&T building in New York City with a top that makes it look like a Chippendale dresser.
After years of embracing the minimalist style, Johnson found himself rebelling against the form he helped create.
The head of AT&T said, I want to be different from all this boxy stuff like the Seagram building. I said, that's right, let's be different. I went to classical, I went to Hadrian, I went to early Christian churches. Actually, I got that famous cut not from Chippendale, but where Chippendale got it from, which was the pediments of ancient Roman Greeks.
In the last 20 years, builders have erected elegant towers and shimmering spires. Some look more like modern art than skyscrapers. Not since the days of the Woolworth Building and the Chrysler Building have skyscrapers been as free to express themselves. Although born in America, skyscrapers have spread to dense urban centers around the world. But today, developers also have to be sensitive when importing an icon of Western capitalism into a society steeped in tradition. The architects of the Taipei 101 in Taiwan labored to make their building represent more than corporate identity and financial prosperity.
When we start looking at this building, we like to think it's growing from the earth. It's like the bamboo in our culture, which is supple. It bends in the wind, but not breaking.
The bamboo-inspired tower has 8 nodes.
We use the lucky number 8 as a basis for the pod. And we put 8 pods together on top of each other, create this basic form.
The exterior is adorned with symbols of abundance and prosperity.
We added the symbols from our culture, such as ruyi, and the coin, the ancient coins, all to make it with a very strong characters based in our culture. I think the design is the soul of a building.
To me, architecture is like film. If it's a really good film, not only is it coherent, but it finally really somehow moves you in that coherency and it says something. It speaks to you somehow. Ditto architecture.
But today, the design of a building must be more than an aesthetic consideration. Increasing energy costs and dwindling resources necessitate more environmentally conscious construction. The latest trend in skyscraper architecture? Sustainability. More and more buildings are going green. In the last century, technology allowed buildings to grow to mammoth proportions. Architects sealed up structures thanks to the introduction of mechanical heating and cooling. In the process, they tossed aside alternative forms of climate control, such as awnings for shading and operable windows that help define building exteriors. But comfort and architectural freedom came with a price. Big buildings have voracious appetites.
I think one of the most dramatic things that we have to realize is buildings account for more than a third of all energy used today in the United States.
We know that cities must be built with density. The question now is, how do we make tall buildings that are sustainable, that are environmentally friendly? And that marks the quest for architects and designers in the construction of 21st century skyscrapers.
The trend began more than 25 years ago, when conscientious designers, engineers, manufacturers, and builders started working together on a different kind of green revolution. The goal? Build more sustainable or green skyscrapers. In 2000, the U.S. Green Building Council established the LEED Green Building Rating System, a benchmark by which a structure's sustainability can be measured.
The LEED Building Rating System, which is an acronym for Leadership in Energy and Environmental Design, was essentially developed to help transform the marketplace towards green buildings.
Studies show an investment of less than 2% of the price of the building can produce a structure that uses 30% less energy and 50% less water. Conservation was a principal objective for the state of California on the Caltrans project. The structure will be one of the largest, greenest buildings on the West Coast. Accomplishing that task means that the building's exterior will be completed in a most unique fashion.
The focus generally in sustainable buildings is to in fact develop a high-performance facade, or a facade that optimizes heat gain and heat loss.
An enormous amount of interior heat or cold escapes through the skin of a building. In addition, direct sunlight creates unwanted heat in the summer. To minimize the solar gain on the Caltrans building, Morphosis architects are using 181,000 square feet of perforated aluminum cladding called scrim as a shading mechanism.
Okay, here we come, Al. Ready? What I'm doing here is checking the scrim panel to see if it lines up with the latching arm. And what we're doing here today is installing this pneumatic actuator. And it will control the opening and closing of the scrim panels. And that's all controlled again through a computer. Kurt, can you go ahead and close the scrim panels? We have 1,031 actuators throughout the whole job. Okay, all the scrim panels look like they closed and the latching arm latched.
The scrim panels over the windows open or shut depending on the time of day and the position of the sun. In addition to shading the building from direct sunlight, they also help to keep the building cool in another novel way. The scrim covers the entire east and west sides of the building and stands out 10 inches from the exterior walls. In essence, this creates a chimney. When the sun hits the scrim, it heats up the air in between the scrim and the building. The hot air rises and pulls cooler air from below, driving what's known as a stack effect. And that's not the end of the exterior's green design. The electrical contractor is covering the south side of the building with 43,000 photovoltaic solar cells that convert sunlight directly into electricity.
What we're looking at here is a photovoltaic system that is going to help cut down electrical costs to this building, and it will be producing about 85,000 watts of solar electricity. Each individual panel creates 28 volts. This system, if it was in the sun all day, could run, say, 40 homes.
Designers hope the environmentally friendly features of the Caltrans building will help earn the building a silver LEED rating. But another skyscraper 3,000 miles away will be pushing green buildings to the max and into the sky. The Durst organization is developing the 54-story One Bryant Park building in New York City, which they hope will be the world's first high-rise to reach the coveted platinum LEED rating.
And there was absolutely no question that this building has to have a platinum rating. That was the goal set by the whole team. And we want to set an example for others that will change the marketplace.
Designed by Cook plus Fox architects, the building will use significantly less energy and consume far less water than other buildings of similar size. Insulated floor-to-ceiling windows will admit as much sunlight as possible. Interior lights will adjust automatically to the amount of daylight coming in. On top of the building, there's even going to be a vertical axis wind turbine.
The building is actually this faceted crystal, and there's a tall mast and a shorter mast. The shorter mast is actually intended to be the wind spire, the element that generates energy through the wind.
We're putting all of our emphasis on doing sustainable buildings because this is the right thing to do.
Using promising projects such as One Bryant Park and the Caltrans building as examples, environmental advocates are hoping green construction will continue to grow. By the spring of 2004, the outside of the Caltrans structure looks almost complete. Although the internal systems aren't finished yet, our building now has a face. A design that's both innovative and environmentally conscious. Its builders are already prepared for the reviews that accompany the completion of any megastructure.
There'll be a certain amount of people look at this building and love it. Some will hate it, and there'll be some in between that go, well, that's the ones that are hardest for me. See, that's the one I'd get, then I'd go, I'm not doing my job.
The Morphosis architects have designed a state-funded building, which is the model of efficiency, while still holding fast to their personal design convictions. Architects through the ages have always faced tough design decisions. Functional or fun? Elegant or economic? Classic or iconoclastic? Maybe the best buildings are all of the above.